Now we continue to solve this optimization problem in the case when win probability P is between 1/2 and 1. We now already know the maximum value of this function over here when P is between 1/2 and 1. So we're going to write down this one over here. V1 of x is equal to log x and plus the constant we have found, C. Remember, the constant C is equal to log 2 and plus P log P and plus 1 minus P and log 1 minus P. And we know this value is going to be positive if P is greater than 1/2. If it's 1/2 is less than 0, so let's put this one over here. Okay, so that's what we have. Now, what does that mean? It means if we use the log as our utility function, this is going to be the optimal expected utility if we are allowed to play just one game and with the initial amount x over here. And we also know what is the optimal bet, because we know alpha star is equal to 2p minus 1. What it means is that the optimal bet size, y star, we say it's the optimal one, is equal to 2p minus 1 times x. Now, because 2p minus 1 is between 0 and 1, so this is the amount we should bet. Okay. Regardless how big the p is going to be, how close to 1, say, you should not put all the money you have in the bet. That's the conclusion. Now, what if we are allowed to play more games, more than one? Then we use the idea of dynamic programming. Let's assume that we can play 2 games, and this is the setup we had before. So if you're allowed to play 2 games, so you're going to decide, first you have amount of money x over here, and you're going to actually bet y over here. You don't know how much, but y is between x and 0. Y over here is our action variable, right? This is our action variable. Okay. And if we bet y, then we have 2 possibilities. We have win and we have loss. If we win, then we have x plus y. And if we lose, then we have x minus y. Now, we have another game to play. So for the other game, x plus y or x minus y becomes the initial value. And the optimal expected utility is the one we have solved, v1 of x. So in the case of win, this part, the expected optimal utility from playing one more game is going to be v1, but we put x plus y inside, because for our second game or our last game, we have this amount. And if we lose the first game and we still have the second game over here, but now we don't have that much money left and we still have one game to play. Remember, this one over here indicates we have one game to play, initial values over here, optimal utilities. So now what we have? We have w over here, given initial value x and one bet y. This is the expected return. So we have p over here, but then we have v1 of x plus y left, okay, and then plus 1 minus p, and then we have v1 x minus y. So that's the one we have. That's why we have v2 of x. The optimal expected value of returns from playing 2 games with the initial amount x is going to be the maximum value over here for y between x and 0. So we are only making the optimal selection for the first game over here and leave the second one for v1 to take care of. and then we have p over here, v1 x plus y and plus 1 minus p and v1 of x minus y. So that's what we have. Because we have solved v1, so v2 can be now solved. We just plug in the function v1. Remember, v1 is log x plus a constant c. So we use this function and we find v2. This method is called backward substitution because you are solving v1 first, and then we have the maximum value y over here less than or equal to x, and then we put this function inside. So this is going to be log x plus y. Whenever you see x over here, you replace it by x plus y, right? And this is plus c, and that's v1 of x plus y, and then we have 1 minus p over here, and then we have log x minus y and plus c. It's the function that we have solved, v1, we plugged in. Now if we look at this one over here, we have p times c, and then distribute 1 minus p to another one. We again have a convex combination of c, so pc plus 1 minus pc, so it's equal to c. C is a constant, so we have this one over here. We have c out and plus maximum value, and y is less than or equal to x and greater than or equal to 0. And then we have p over here, log plus y and plus 1 minus p log x minus y. And see how lucky we are, because look at this maximization problem over here. This is exactly the same thing we saw when we were solving v1 of x. Since we have already solved v1 of x, so we can simply use the previous result. So this is going to be c plus, we know what it is, this is going to be log x and plus c. So we have log x and plus 2c. And we can easily spot the pattern, and then we can say by using mathematical induction we have the following. By induction we have Vn of x. We solved it, and perhaps we can write down the formula again, because it means we have n games to play, and then we have the following structure. First, we're gonna play y again, the bet. If we win, we get x plus y, but then we have n minus 1 game to play. But that's when we win, right? And if we don't win, then we have x minus y left, but we still have n minus 1 games to play. And the probability to lose, we know it's 1 minus p. So this is again a very similar setup. So we have y is less than or equal to x and greater than or equal to 1. Okay. And by using the induction, we will see this is equal to log x plus nc. C is the same constant that we had over here. This is a constant. So that solves the problem completely. So what is again Vn of x? This one over here, we know the following thing. This is the optimal expected value if we have n games to play and we start with initial amount of money x. So this is log x and plus nc. And that's the case when p is greater than or equal to 1/2. And for p less than 1/2, we have a different conclusion over here. So this is p greater than or equal to 1/2. That's the one. Okay. All right.